Young's double slit experiment. We have earlier discussed the phenomenon of interference of waves. Therefore, it is natural to expect that light also exhibits the phenomenon of interference. But interference of light is not so evident as the interference of sound waves. This is due to the very small wavelength of light waves as compared to the wavelength of sound waves. In 1801, Thomas Young demonstrated successfully the interference of light by performing a double slit experiment. Young allowed sunlight to pass through a hole and then at some distance through two pinholes, S1 and S2. When light was received on a screen, an uneven distribution of light intensity was observed on the screen. A number of alternate dark and bright spots were seen on the screen. The phenomenon of interference can be understood on the basis of Huygens principle. The secondary wavelengths coming from S1 and S2 have equal amplitude, velocity and wavelength. In figure, the continuous circular arcs represent the regions of wave crest. The dotted circular arcs represent regions of wave trough. At points marked by small circles, the trough of one wave is superposed over the trough of another wave, or the crest of one wave falls over the crest of another wave. According to the principle of superposition, the amplitude and hence the intensity of the resultant wave is maximum at these points. Similarly, the intensity is minimum at points marked by a cross. Thus, the resultant intensity is maximum along the lines connecting the crosses. On the screen, we get a number of alternate dark and bright regions of equal width. This is called interference pattern. Analytical treatment of interference. In the experimental setup, we use a sodium source of light. It gives an intensively bright golden yellow light. Ahead of this source of light, we have a single slit. It is rectangular and arranged vertically. It is nearly 1 mm wide, symmetrically to S. There are two slits, S1 and S2, which are nearly 0.3 mm wide. The distance D between the two slits is nearly 1 mm. A screen is held parallel to the slits at a distance of nearly 2 meters. The above arrangement ensures that light waves coming from S1 and S2 in the same phase. So, S1 and S2 are coherent sources. Let us consider a point P on the screen. When either S1 and S2 alone is open, there is a continuous full light all along the screen. However, when both the slits are open, this uniformity disappears. Instead, we have a set of alternate bright and dark vertical lines, equally thick and equally distant from each other. These are called interference fringes. In arriving at P, the waves from S1 and S2 have to travel different paths. So, the waves arrive at P with a certain path difference. If path difference is equal to n lambda, or phase difference is 2n pi, then the two wave trains reinforce each other, giving a fringe of high intensity. If path difference is equal to n plus 1 by 2 into lambda, or phase difference is n plus 1 by 2 into 2 lambda, that is 2n plus 1 pi. Then there is destructive interference between the interfering wave trains, and we get a dark fringe.